In this lesson, we're going to finish up with talking about transformations for now, although we'll be using transformations throughout this course. But in particular, I want to look at doing transformation of exponential and sinusoidal functions. We, in fairly recent lessons, just learned what an exponential function is. It's one of those ones that grows quickly up to the right, or else if it's decay, it goes quickly down from the left to the right. Sinusoidal functions we saw in general are a type of periodic function. They have that wave shape. So let's start with exponential. We'll take them one at a time. So the idea of transformations is the same whatever our parent function is. A, K, D, and C are always going to be what we're looking for. It's just a matter of where we see them in a particular type of function. So maybe for this lesson, I'll just pick some highlighters, and I'm going to highlight A, vertical stretches in yellow, K, which we know as horizontal stretches and reflections in green, D will be our horizontal shifts. I'll do that in blue, and I'll use orange for C, our vertical shifts. So state the transformations for the following, also state the domain and range. So again, this is a particular formula that is specifically for exponential. In other words, if you look at it, then you'll see that it's just, if I take away the A, K, D, and C, what I've got is the original function, which I'll just do over here on the left, which is y equals b to the x. Really, that's all that's left if I take away a, k, d, and c, isn't it? And we recognize that that's our parent function for an exponential function. So I look where different numbers are in a function to decide if they're a, k, d, or c. In this case, for the first example, we can see that it's got a base of 5, right? So the number that the exponent is on is our base. So the base is 5 in this case. The other things that are with it, in this case, is a number in front. That's in the A position. So that means that it would have a vertical stretch by a factor of 2. Vertically stretch by 2. If we know that our parent function, again, I'll sketch this over on the right, looks like this. So if y equals b to the x, if this is just some generic exponential growth function, remember the domain for the parent function was all real numbers, and the range was all real numbers that were greater than 0. Not equal to 0 because that would mean it would have to touch the x-axis, which it doesn't. So what does a vertical stretch by a factor of 2, going back to our example, do? Well, it just makes everything higher up, but it's not going to drop below the x-axis. It's still going to have a domain of all real numbers. In other words, the domain is going to be exactly the same for this function as it would for the parent function. It's all real numbers for the domain, and the range is still going to be all real numbers greater than 0. It's just that the range is going to grow faster, but in the end, it's just going to keep going forever. Looking at the next one, we've got this negative, it seemed to be a -1 in front of the parent function. The parent function is 3 to the x, and we've got this +7 at the end, which is outside of the function. So we have an a value of -1, we have a c value of 7. So we know that the -1a value is going to give us a reflection. It's a vertical reflection, which means it's in the x-axis. And the +7 c value is going to shift it vertically. So in this case, since it's plus, it's going to be up 7 units. Again, go back to this graph here. Well, let's actually sketch it. That's probably the easiest way. So if we take that parent function, which I just scrolled off the top of the screen, and I were to reflect that in the x-axis, now it would be down here, right? But then if I was to shift it up 7 units, it would look something like this. It would have a horizontal asymptote at 7. So it could never get up to 7. It's always going to be below 7. So how does that affect the domain and range? Well, it doesn't affect the domain. The domain is all real numbers still. But the range, of course, is affected. It's all real numbers, but with a restriction. Again, it's below the asymptote, so it's less than something, and that something that's less than is the 7 that it was the new horizontal asymptote is. Looking at this one, again, what do we have? Well, there's nothing in the A position, right? There's nothing here. There's no transformation here, so we can skip that. But there is definitely something in the D position and something in the C position. That one I've highlighted in blue, to be inside the function, as I often describe the K and the D values, to be inside the function in this case means to be part of the exponent. It would be K if it's a number in front of the X, and it's D if it comes after the X. This is clearly a D. But we also remember that when we take D out of the equation, then we have to change the sign. We don't do that for C. So our D and C values are -4 and -3 respectively. So we have a horizontal, let's say it in a different way. Let's just say shift left 4, because the -4, negative shifts to the left and 4 units. And we're going to shift down 3, because that's what C values do. They shift up and down, and the negative makes it go down. As far as the domain goes, let's do a quick sketch again. Picture the parent function. What happens if I take the parent function, shift it left 4? Well, now it's, everything's gone over to the left, and it's gone down 3. So we have a new iPad's acting up. We have a new horizontal asymptote at -4. And everything shifted to the left a bit. So this is just a very rough sketch, but it gives you the idea of what's going on in general. The domain is all real numbers. Even though my sketch doesn't show it going all the way to the right, if I go far enough out, it's definitely going to keep going out to the right forever. The range is still above the asymptote in this case, and it's the, did I say -4? There, I did make a mistake there. The 4 was to the the 4 was to the left. It was down 3, wasn't it? Let's see if I can delete that. There we go. It's -3 that the horizontal asymptote is above. So y is all real numbers as long as they are above -3. Again, it's not touching -3, so I won't put the equal sign there. This last one, there's something funny that we have to notice about this one. Take a look back at the original formula. In particular, notice how K value is common factored out from the X minus D. So it's K bracket X minus D end bracket. That matters. That's the format we have to have it in to make it work. In this case, it hasn't been common factored yet, so I have to do that. So I'm going to rewrite this first as 3 times 4 to the 2 bracket X minus 3, because I've taken the 2 out as a common factor. And again, now I can see that my A value is 3, my K value is 2, my D value is +3 when I take it out. +3. So what happens, and I always do my transformations from left to right. In other words, I'll start with my stretches, my A and K, and then I'll talk about my shifts afterwards. So it is vertically stretched by a factor of 3. It's horizontally compressed you could say by 2. I would probably just say by 1/2. This terminology sometimes confuses people when we talk about horizontal compressions. The K value is clearly 2. If I say it's compressed by 1/2, sometimes they wonder, what does that mean? All I want you to remember is that, any K value bigger than 1 is actually going to make something smaller. So a K value of 2 will make it half as wide. So to me, that's the clearest way of saying it. The key word, though, is I need you to tell me that it's compressed, because it's definitely compressed with a k-value of 2. If you told me it's compressed by 2, I would probably know what you meant as long as you used the word compressed. But I think it's clearest to say that it's compressed by a half, meaning that it's half as wide. And it's shifted right by 3, because the d value is positive 3. So a sketch of that shows, again, think of the original one. It's vertically stretched. Okay, so it's taller and skinnier. Compressed, so it's half as wide, so it looks even skinnier still. That's going to make the graph, basically a graph that starts out like this is probably going to end up looking more like this when you do both the vertical stretch and the horizontal compression in there. But in general, that's not going to affect my domain and range. And then it's going to be shifted 3 units to the right. So I'm going to take that, what I've done in red, and just move it 3 units right. And so it's going to look sort of like this. Again, really rough, but enough so that you can do the domain, which is still, as you can see, it's been all real numbers for all exponential functions, and that's always going to be the case unless there's some other external restriction. And the range actually wasn't affected at all, was it? The only thing that's going to affect the range is if it's either reflected in the x-axis or if it's shifted up or down. Neither of those things happened in this case, so the range remains y is greater than 0. So there you have transformations a, k, d, and c for exponential functions. Transformations are transformations no matter what kind of parent function we start with. So from our previous knowledge of transformations, as in a couple minutes ago, we still know that a is what comes first. It's the vertical stretch, and it's the reflection in the x-axis, vertical reflection. K is still the horizontal stretch, and when I say stretch, I mean stretch or compression. It could be either one. I'm just using stretch to include all those terms. And it's a reflection in, maybe I should say, in x-axis, because that's a vertical reflection. This one's a reflection in the y-axis. That's a horizontal reflection. D, of course, is my horizontal shift. And C is my vertical shift. So nothing is different as far as what A, K, D, or C stand for. They're always the same. All that matters is what parent function I'm working with. Well, in this case, I'm working with the parent function of y equals sine x. And you'll remember from a previous lesson that y equals sine x looks like this. Again, let's do a rough sketch. There is one cycle. It goes from 0 to 360 degrees. 180 degrees is the middle. The maximum was 1. The minimum's -1. The maximum occurs at 90 degrees. The minimum occurs at 270 degrees. That is our parent function. I guess I forgot that the very first thing that we want to do for this part is look at it here. So, well, let's do it one more time. It doesn't hurt. Let's say this is 1. We don't have to say that's 360. I'm just going to re-sketch it here, but using the scale. I'm going to assume that this is 1 and this is -1 here. So I'm going to use this scale. So it's going to be a more compressed version than my rough sketch I just did over on the right. But it's got the exact same information on it, doesn't it? A, the amplitude, remember A is vertical stretch, but A is also amplitude as far as periodic functions go. So the amplitude is 1 unit. The period is 360 degrees. In other words, one cycle starts at 0 and goes up to 360, and then it would repeat, assuming that we keep going. And the axis of the curve is that line that goes right down the middle like this, and that's on the x-axis, which is represented by the equation y equals 0. So if I want to do some transformations on it, again, what I'm looking for is where the different numbers are. So y, or g at x, whatever, equals sine 2x. Where is that value found? Where's that 2? The 2 is the new thing, right? That's what I'm focusing on. It's not out front, which would make it an a value, but it is inside the function, but in front of the x. That makes it a k value, and that's all we have. So the k value is now 2 instead of 1. So if I was to graph this, that would compress everything. They'd compress the graph in half. So instead of doing one full cycle in 360 degrees, I'm going to do one full cycle in half of that, which is 180. So everything is going to get compressed in half. So the midpoint, instead of being at 180, will be at 90. The maximum, instead of being at 90, will be at 45. The minimum, instead of being at 270, will be at 135. There's one cycle. And this little formula here, it talks about the period. If we're compressing things by the k value, right? K value always, a k value of 2 will compress something in half, a k value of 3 would compress it into a third, and so on. That means if we've got a periodic function, we can get the period of the new function simply by doing 360 divided by k. So our parent function has a period of 360, but if we're compressing it in half, then obviously half of 360 is 180. So there's my new sketch, and that's just one cycle. It's always a good idea to fill up the graph. So if I was to fill in this grid and just keep, I just repeat this. Just repeat this until I filled in the entire grid. And I'd put arrows on the end. I like to do that. So there is my new sketch. All right, what's new for this one? Well, it's got a 3 for its a value. Still has the same k value of 2. So we know that it's still got a period of 180, but the vertical stretch is 3, so it's going to become 3 times as high, 3 times as stretched vertically. That means I can just stretch the amplitude. The amplitude for our parent function is just 1, right? It's just got a value of 1. So to stretch it by 3 simply means make the amplitude equal to 3. And if the axis of the curve hasn't moved, then that just means all I have to do is make all the points that are off the x-axis 3 times as high. So again, it's going to go from 0 to 180. It's going to have the maximum at 45 degrees, but now instead of being at 1, it's going to be up at 3 times as high. And the minimum, instead of being at -1, is now going to be at -3. So now we've got a graph that looks like this. And again, I could extend it to fill in the rest of the graph, which is a good idea. And when I do that, I get this. So again, now we've done a transformation that involves a and k. Well, what if we add some other stuff in here? Here's one extending it again. Still got an a value of 3, still got a k value of 2, but now it's got a d value. D is 60 degrees. Remember, for d values, they have to be inside the function, which this is. In other words, this 60 degrees is clearly inside the brackets. We're taking the sine of it. In order to be a c value, it would have to be outside brackets after we've done the sine. So this is a d value, and we need to have it in factored form. Notice how it says 2 bracket x minus 60 degrees bracket. So that is definitely a d value. It's in the proper form, and so we can see that d equals 60 degrees. Remember, we change the sign when we take it out. So what's this about phase shift? Well, phase shift is just a fancy term for periodic functions for the horizontal shift. So the phase shift means horizontal shift when we're talking about periodic functions. So phase shift or a d value of 60 means that we're moving right, shift right 60 degrees. Now 60 degrees, remember, this axis here is angles. So when I say shift right 60 degrees, it just means move 60 degrees along that number line farther to the right. So if I were to take this graph here, the only thing that's new on the last graph, number 4, is this shift. So if I were to take that graph from number 3 and take each of those points and move them 60 degrees to the right, I'd have my new graph. So the point 0, 0 will shift over to 60, 0. And the point, and the point, how am I going to do this? And the point 45, 3 is going to shift over. I'm going to add 60 degrees to 45, which will take me to 105. An easy-ish way to do horizontal shifts, you just figure out what one unit on the scale is. So in other words, from here to here, where I'm highlighting in yellow, is 30 degrees. So if I have to shift right 60 degrees, I'm going to shift all my points 2 blocks to the right. So with that in mind, that means this one that's at 90 is going to shift 2 blocks to the right, and it's going to be at 150. And this point here that was at 135, I guess, it doesn't really even matter. I just have to shift 2 blocks to the right. So this is going to go a little bit past 180. And then the 180 is going to shift 2 blocks to the right, and so on. So here's my shifted graph. So everything's been shifted 2 blocks to the right, because 2 blocks on this scale is the 60 degrees I need. But again, I wouldn't just do one cycle. I really should backfill it. So if I had to go back 60 degrees, then, I'd probably get to a minimum about here and here. And my maximum, which was at 225, is going to move over to just past 275. And here we go. So here's basically what the sketch looks like if I fill in the rest of it. So that's how we can do transformations of sinusoidal graphs, exactly the same as you do exponential graphs, exactly the same as we do any kind of function. Any function can be transformed using those same A, K, D, and C values. We can also use them, A, K, D, and C, to work backwards to help us create equations from graphs. So here's an example. A nail located on the circumference of a water wheel is moving as the current pushes the wheel. So picture some sort of old-time mill on a river with a giant water wheel being pushed by a current. But it's got a nail on it. So we're watching the nail, and so it goes up, it gets to the top, it starts to come down, it goes underwater for a while. That's what they're talking about. So it's modeled by this graph. So you can see on the graph, we've got the height of a nail as time goes by. I don't know if this would be, I assume this is seconds, maybe? Minutes? I don't know how slow this water wheel moves. Anyway, it's time in some units. The maximum height is 3 centimeters. Oh, this is a very tiny wheel, isn't it? I guess it's seconds. So we got 3 centimeters. The highest this wheel goes is 3 centimeters above the water, and it goes 1 centimeter below the surface of the water. All right, so we can see it's a periodic function. As time goes by, the wheel spins. We're starting at the top, the nail's starting at the top. As time goes by, the wheel spins, it starts to go down, it dips under the water here, gets to its lowest point, starts to come up again, gets to the top again. It's just going around in a circle, so this nail just goes down and then it goes up as the wheel spins around, right? That's the situation. We want to write an equation for this. We can work backwards to write the equation based on knowing A, K, D, and C. So we need to determine certain things. And again, this is the order that it'll help us to do it. So first we want to find the C value. Why? Because the C value is going to be the axis of the curve. Why is the C value going to be the axis of the curve? Well, remember, if I go all the way back to my original sketch here, the axis of the curve was y equals 0. So if I look at this particular graph, obviously the axis of the curve isn't at 0. Wherever the axis of the curve is, and just, it's somewhere up here, right? Well, wherever the axis of the curve is, it must have been moved up by that amount. And the only thing that's going to move it up is the C value. So if I can find out how much the axis has been moved up, then I know what the C value is. So that's the thinking here. So I could use the formula, or I could just be careful and just count squares on the graph. But as far as the formula goes, remember it's y equals the max plus the min, which is -1 divided by 2. So that's 2 divided by 2 is 1, so y equals 1. So the axis of the curve is here at 1. Again, we could have figured that out just by counting the squares. There's 4 squares above and 4 squares below the axis, but I use the formula. That is my C value, because in order to get the axis from 0 up to 1, it must have been shifted up by 1. So the C value is 1. Now that I can see what the C value is, then it's pretty easy to see the amplitude. I can tell the amplitude is 2, can't I? Amplitude is the distance between the max and the axis, or between the min and the axis, or I could use the formula A equals the max minus the min divided by 2. So that would be 3 plus 1, which is 4 over 2, or 2. So another way of getting the exact same thing. Remember, on our parent function, the amplitude is 1. So in order to get whatever the amplitude is on our new function, it must have been stretched by that amount. And so since this one's got an amplitude of 2, it must have been stretched by 2. So A equals 2 is my vertical stretch. So there's my A value. Okay, so I'm just gathering A, K, D, and C so that I can then put it into an equation. Determine the K value by calculating the period formula. All right, so what's one cycle on this graph? We know that normally the period is 360 degrees, right? Well, let's see how long one cycle. We start at the top, we go down, we come back up. There's one cycle, and it occurred after 10 seconds. So how would we go from 360 to 10? Remember this formula up here that I highlighted in pink? So the period equals 360 divided by K. Think of that as a formula that we can use over and over. Let's put a box around it, because that's how I like to recognize formulas. So there's my period. Period equals 360 divided by K in general. Okay. So let's start with that. Period equals 360 divided by K. I want to find out what K is. I don't know what that is, obviously, but I do know, as I just pointed out, that the period is 10. So I can plug that into my equation for period. So if period equals 10, then I can rearrange to isolate for K. If I multiply both sides by K, I get 10K equals 360. If I divide both sides by 10, then I'll have K isolated. So 360 divided by 10. So K equals 36 degrees. I'll be honest, when I'm doing a K value, I don't usually bother to put degrees on it like this, so I might just say K equals 36. So K equals 36. I'm just going to say, now I've got 3 out of my 4 values that I need to know in order to write the equation. The last thing I need to know is the horizontal shift. Horizontal shift depends on whether you're using sine, cos, and it says or negative sine and negative cos. I'm not sure. I think I'd stick to just sine or cos. So decide whether you want to use sine or cos. So in other words, look at the graph. We know that a basic sine curve starts on the axis of the curve and then goes upward. Remember what the basic cosine curve looked like? The basic cosine curve, I'll just do it here as well, looked like this. It was exactly the same as far as the period goes. Pardon me. It was 360. It had the same maximum of 1, the same minimum of -1. Everything was the same except where it started. It started at the maximum, went down to the minimum at 180, came back up and hit the maximum again at 360. So the only difference was that it was shifted compared to the sine curve. So what we want to look at in our function below is, where does our actual graph in our question start? Does it start either at the maximum, like this one does, or the minimum, which I could easily get with a reflection, or does it start in the middle, like this one does? If it starts at the maximum or the minimum, I'd go with the cosine curve. If it starts at the middle, I'd go with the sine curve. Well, looking at this one, it's clearly starting at the maximum, so I would go cosine for this one. And the fact that this one starts at the maximum and that cosine, the parent function of cosine, starts at the maximum means I don't even need to do anything to it, right? They're starting at the exact same place. So say my graph started over here, and it was cosine, and it was something like this, well, then I'd have to do a d value. I'd have to do some sort of horizontal shift to shift my parent function to get over there. But I don't even have to do that in this case. There's no horizontal shift needed to make this look like a cosine curve. So I'm going to start with cosine. I'm going to use cosine, that is, because it starts at the maximum. No phase shift is needed, no d value, so I'm just going to say d equals 0. So plugging everything into the equation, remember it was f at x or y equals a cos k x minus d plus c. All right, here's the big moment where we put it all together. So a was 2. Let's highlight again. So much fun. So a was 2. K was 36. D was 0. So it would be minus 0 if I want to actually plug it in. Normally I wouldn't write that down because I just know that that doesn't make a difference. But I'll put it in for the sake of the lesson. And C was 1. So then I could simplify that down to y equals 2 cos 36x. I don't need the second set of brackets if d equals 0. And that would be my answer for that one. Oops. And last example. A sinusoidal function has an amplitude of 2 units, a period of 180 degrees, a maximum at 0.3. Sketch 2 cycles of the graph. Well, we've already done this kind of stuff. This is not transformations. Well, I guess it kind of is, but really it's just using our common sense and putting things together. So remember, when I first talked about periodic functions, that's the word I'm looking for, I said we should do things in a certain order. We should figure out where the axis of the curve is, then we should look at the amplitude, then we should look at the period, and then the number of cycles. So what do we have here? We do have an amplitude given, we've got a period given, and we've got just a maximum given. Well, that is enough to get me going. I guess I want to do it in slightly different order, but I can use the maximum, which is 3. So let's start here with this maximum of 3. I'm going to erase that. That's just a guideline. So if it's got a maximum of 3, then that means that I put that together with the amplitude of 2, and I count down 2 from 3, then that will take me to where the axis of the curve is, right? I said I wanted the axis of the curve first, so I can use it, do a little detective work, and put the maximum and the amplitude together and come up with the conclusion that the axis of the curve has to be at 1. That way, if the axis of the curve is at 1, when I have the amplitude of 2, it'll go up to 3 as the max. It'll go down 2 from there to -1 for the min. The period is 180, so it's going to all fit one cycle in here, and it has the point 0.3. It's giving us that very specific point of 0.3, so it's even telling us where it starts. So if it starts there, that means if one cycle completes, it has to end there as well, and halfway between 180 and 0 is 90, so the minimum has to be at 90, -1. It's going to hit the axis of the curve halfway in between those things at 45 and 135, and so there's one cycle. And then the last part is it asks me to do 2 cycles, so I'll just repeat. So it seems every 3 units, I can do a new point at the appropriate place. And I'm going to end up at 360 for my second cycle at the maximum of 3. So again, it's just putting all the different parts together. In order to do this, you have to be very clear on A, K, D, and C. But if you are, then it all fits together nicely.